The other factors that affect ionization energy would be the completely filled and half filled orbitals have lower energy. So the removal of an electron to achieve this half filled orbital requires usually low energy. So let's look at what do we mean by completely filled and half filled. So let's look at a 3D sublevel. And we know that the D has 5 orbitals, 5 boxes, 1, 2, 3, 4, and 5. Okay, and let's draw one more, which is this. This is 1, 2, 3, 4, and 5. Let's put electrons in them. Okay, so this is 1, 2, 3, 4, and 5. So this would be 3D5, and this is half filled. And 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. This would be 3D10, and this is completely filled. So these are much more stable as compared to incompletely or partially filled d orbitals. And same is true for the p orbitals. So if we were to draw 3p, and we know that p sublevel has 3 boxes, and this is half filled. So this would be 3p3, and this is much more stable than incompletely filled p orbital. And again, if we have this is again, we can say this is 3p6. That means there are 6 electrons in this. 1, 2, 3, 4, 5, and 6. This is much more stable, and this is also stable as compared to incompletely filled p orbitals. So to remove an electron from these more stable electron configuration would require more energy, and that's what we are going to see on the next slide. So we have a graph of atomic number and ionization energy. Okay, and if you look closely, this is period 1, this is period 2, and this here is period 3. So the trend for periods is, for ionization energy, is that as we move across a period, the ionization energy is increasing, and that's a general trend. We see that from lithium to neon, that the ionization energy is increasing. It is increasing. Okay, but within that period, we see that beryllium has a little bit higher ionization energy as compared to boron. And the reason is because of the electron configuration. Beryllium has this electron configuration, and it's 1s2, 2s2. This is completely filled, and it would require more energy to remove electrons from beryllium as compared to boron. Okay, and then if we look at nitrogen, this is electron configuration for nitrogen: 1s2, 2s2, 2p3. 2p3 means it's half filled p orbital. It's much more stable and therefore would require more energy as compared to oxygen to remove that first electron. Okay, so half filled and completely filled orbitals are much more stable and would require more energy to remove an electron as compared to incompletely filled orbitals. Let's discuss what's happening from helium to lithium here. So we see a big drop in the ionization energy from helium to lithium. And the reason is helium is in period 1 And as we move to lithium, we are now in period 2. Okay, and we can see that from the electron configuration also. This is the first energy level, and then lithium has 2 energy levels. So this electron, which is the outermost electron, it is easier to remove the outermost electron from lithium is because this electron is further away from the nucleus, and therefore less energy is required to remove this electron here. Okay, and the same is true when we compare neon to sodium. So the neon electron configuration is 1s2, 2s2, 2p6. There are 2 energy levels. So in the first energy level, we have 2 electrons, and in the second energy level, we have 8 electrons. When we move to sodium, now we are in period 3, and there is another energy level that has been added, which is n equals to 3. Now, this electron, which is present in the third energy level, is far away from the nucleus, and therefore it's easier to remove this electron as a hold of the nucleus on its electron is less. And therefore, we see a big drop in the ionization energy from neon to sodium. So let's summarize what we learned so far. So the trend for ionization energy, and we're discussing about the first ionization energy. The trend is that as we move across, the ionization energy is increasing. And as we move down a group, the ionization energy is decreasing. Okay, so and that would be the general trend. So it increases this way on the periodic table.